Okay, let's start. My name is Wei. I'm a graduate student of Professor Zakar. And because Professor Zakar is out of town today, so I'll teach this lecture. Today we'll talk about image coding. So the objective of image coding is that we try to compress an image. So what we mean by compress is that we represent an image with as few bits as possible in order to that, but still in the meantime we still preserve the required quality. So we do not lose much quality, but we reduce the bits to represent an image. And there are three main components of an image coding system. The first one, we want to know that what would we code for an image. So basically there are several possibilities. The first one is that we could just code the image directly, which means that we could code the image intensity directly, like the pixel value. And also, the more popular approach is that we first do a transform for the image, and then we code the image transform coefficient. We code the transform coefficients. And also, today, in a more advanced image coding technique, we first model an image first, and then code the model parameter. So it depends on the model. If we try to code just a circle, maybe, so all we need to is code the center, the position of the center, and also the radius, r. And the second component of an image coding system is the quantization. The problem that the quantization tries to solve is that how to assign the reconstruction level to each value. I mean, in reality, generally the value is at analog, or they require lots of bits to store it. By quantization, it reduces the bit to store the image. By doing that, actually, we reduce the bits in the cost of losing some information. So quantization generally means lossy compression. And there are two basic approaches of quantization. The first one is we just assign uniform spacing between two quantization levels. So this approach is very simple. And also the second one is that we try to optimize the performance by minimize some error criteria so that the spacing between two quantization interval is non-uniform. I'll cover these two approaches in more detail soon. And also the third component of an image coding system is bit assignment. Also, we call it code word assignment, which means that after the quantization, we have some integers, but we need to know how many bits we assign to each quantization level. And also, these have two approaches. The first one is that we just assign equivalence bits to each quantization level. And the second one is that we assign unequivalence bits, which is more complicated, but maybe more efficient. So I'll cover these two in more details in this lecture. Now I think I talk the quantization. First, I talk the uniform quantization. Here we have two assumptions that to simplify the explanation. The first one is that we just directly encode the image intensity. And the second one is that we assume that we use simple equivalence bit assignment for this stage. And quantization, we have scalar quantization and also the vector quantization. By doing the scalar quantization, we mean that we encode each value independently without considering the correlation between different values. And vector quantization means that we encode that different scalars together jointly by also considering the correlation between different values. We could possibly improve the efficiency of quantization by doing the vector case, but it's much more complicated. And in this class, I only cover the scalar case. So the uniform case actually is very simple. We assume that F is the image intensity. It's from 0 to 255. And also we have L means the number of reconstruct levels. First, we could compute the distance between two decision boundary, delta, which means that it's the maximum of F minus the minimum value of F divided by the number of reconstruct levels. And using this, we can get the decision boundary and the reconstruct level. The decision boundary is that we have this simple equation, which means the two neighboring decision boundary, the spacing between two neighboring decision boundary is equal to delta. And also the reconstruction level in that region is just the middle point of the two neighboring decision boundary. And here I'll explain this by using an example. Here we have F from 0 to 255. So we have 4 levels. Actually, we evenly divide this interval. So we can get 1 to 128 and 1 to 64, and here this 1 to 192. So these are the decision boundaries from D0 to D1, D2, D3, D4, and the reconstruct level is just the middle point of two neighboring decision boundaries. This is R1, R0, which should be 32, and R1, R2, R3. So 96, 160, and also the 204. Anyway, 224, I think. So this is the uniform quantization. It's very simple and very easy to implement. But the shortcoming of the uniform quantization is very obvious. It's not optimal for most of cases. Actually, it's only optimal for when the distribution of the image intensity is only uniform. So by intuition, we think that here is another example. So the x-axis can be treated as t, or the position, and the projection to the x-axis means that the frequency appeared of these values. So we could see that the value appear more frequently in this region and also in this region. So it's reasonable that we assign more reconstruct level in these two regions and apply less reconstruction level in this region, so that by doing this, we can possibly actually reduce the mean square error between the reconstructed value and the original value. So people propose that we actually do the quantization based on some error criteria. So it's non-uniform case. Non-uniform based on some error criteria. The most popular error criteria used by the society is the MSE, which means that the mean square error. In order to formulate this problem, we first need to introduce several variables. The first one is the auto code is F. We model it as a random variable, which has a probability density PF. PF is the probability density function. And also we use Ri to represent the reconstruction level, and Di to represent the decision boundary. And we use J to represent the number of reconstruction levels. So these are all the variables I use to formulate these problems. So first, I define the MSE between the original value and the reconstruction value as epsilon, which is the expected value between f minus the f hat, which is reconstructed value square. And we can do the integral between f, the minimum value of the f, and to the maximum value of f, as f minus f hat square times pf df. So the problem that I want to solve is that we want to minimize epsilon. So by choosing different Ri and Di. So this is the problem I want to solve. And we know that we have several decision regions. So inside each decision region, actually the reconstructed value f hat is just a constant. So we can further represent this equation into the following equation, so which is just the expanded version of this equation, which is the sum from the first decision region to the last decision region. And inside each decision region, we can just integrate from dj to dj plus 1. These are the decision boundaries. And inside this decision boundary, this original value minus this reconstructed value, just the Rj, which is a reconstructed level, square times pf df. In order to optimize this equation, we take derivatives. So we first take derivative from 2. We first take derivative of dj and let it to be 0. And we could get one relationship between dj and rj, which is that dj is equal to rj plus rj minus 1 divided by 2. So which shows that the decision boundary dj actually is the middle point of two neighboring reconstruction levels. And also we can take derivative with respect to rj and let it to be 0, and we can get another equation. So which means rj is equal to, from the integral from dj to dj plus 1, f times pf df divides dj plus 1 pf df. And this shows that rj actually is the centroid of the probability mass inside this decision region. I think this agrees with our intuition in that we try to assign the more reconstructed level to the place where the value are more likely to appear in order to minimize the mean square error. And the number of these equations are actually 2j, and unfortunately they are not linear equations, so it's not very easy to solve. And in 1960, Max and also in 1957, Lawyer, these two people actually proposed a solution for these equations independently. They solved these equations in an iterative way. So we call this the solution of this equation as Lawyer-Max algorithm. In the book, at the page 595, you see it? So see this table. Actually, it lists the solution for two distributions, the uniform, Gaussian, and Laplacian. And we could see that for the uniform distribution, actually the uniform quantization is already the optimal way to do the quantization. but the uniform but for Gaussian and Laplacian, also, the optimal way is not uniform, is non-uniform. And in this figure 10.5, we could see that how to use the non-uniform quantizer to quantize a Gaussian distribution. So basically, from all the values which is below 1.5, minus 1.5, we will assign the value. Oh, I'm sorry. All the value which is below minus 0.98, we assign the value of minus 1.5, and for all the value between minus 0.98 to 0, we assign the value of minus 0.45. So the spacing between different reconstruction level actually is non-uniform, and also the spacing between the decision boundary is also non-uniform. And the figure 10.8 and 10.6 actually compare the performance of two schemes. One is the layered max quantizer, and the other one is uniform quantization. We could see that in terms of the metrics of the MSE, the layered max quantization outperforms the uniform quantization. And when the number of bits assigned to each value as 4 bits, the number of quantization level is 16, I think the performance gain can be 1 or 2 dB, so which is huge in the compression society. So by taking a look at the table, we can see that for the uniform distribution, actually the uniform quantization is already optimum. So this provides some insight to us, and we can possibly find an alternative way to do the quantization for the non-uniform distribution. So the idea is here. So first we have the f has non-uniform distribution, but we apply some nonlinear function to map f into g. This is some nonlinear function. So the property of g is that g is uniform. And then we can simply apply the uniform quantizer to g and get g hat. We know that this is optimal for g. And then after we get g, we could just apply an inverse of the original transform function. And we get f hat. So we know these two actually do not lose information, and we use uniform quantizer. This is optimal, and we could see that we get an optimal non-uniform solution for f. And there are several choices of how to select the nonlinear function. One possibility is that we choose the CDF of f, which is the mapping function can be the integral from minus infinity to f and times. This is the probability density function of f dx minus 1/2. So by doing this, we can map f to a uniform distribution g. Okay, now I'll talk about the code word design. So the problem of the code word design to solve is that we have the condition. Here is our image coding system. We have an image here, and we'll apply some transform. Generally, we use DCT, and we get some value, and we need to quantize it. here we get some integer values. And then we assign the code word design or the bit assignment in order to get some bits. And now we get the bits as 0010, a string of bits. So now I talk about the bit assignment. Also for the bit assignment, we have two options. The first one is uniform. We just assign the equal number of bits to each quantization level. And we can do it in a non-uniform way. The intuition is that some symbols appear more than other symbols. So we can possibly assign shorter code words to a symbol which are more likely to appear, and assign a longer code word to a symbol which are less likely to appear. So by doing that, in averagely, we could possibly shorten the bit length. So, I mean, reach the effect of compression. And however, so here is one example. And we have 4 symbols. Each has a probability to appear. A can be 1/2, and B 1/4, and C 1/8. So the uniform way is very simple. We just assign 2 bits for each symbol. We can 0, 1, 1, 0, 1, 1, and 0, 0. So the average bits per symbol we can get is 2 bits per symbol. But we could try another way, which is non-uniform. So we can assign A as 0, and B as 1, 0, C as 1, 1, 0, D as 1, 1, 1. And by doing that, we can compute the average bits per symbol by just compute the expectation. So which is 1 times 102 times 2 times 104 plus 3 times 108 plus 3 times 108, which is equal to 1.75 bits per symbol. So by doing this, we actually save 0.25 bits per symbol. And however, using the non-uniform bit assignment, we need to be careful of the code word design. Otherwise, there may be some ambiguity in the decoder side. For example, if I do not use the 111 for D, I use instead of here for D, we use instead of 010. So we can say that when the decoder sees this bit, when these 3 bits, it can either explain these 3 bits as AB, because A is 0 and B is 10, or explain it as D. So this has some ambiguity, and we cannot design the code word like this. So there is some rule, which means the prefix rule, is that we require that each code cannot be a prefix of another code. So the code which agrees this requirement, we call it prefix code. So in order to introduce the code word design schemes, I first need to talk about a little bit information theory. So in information theory, they define an entropy. So I think most of you might have heard about it. So an entropy, H, is just an expectation of log 2 pi. So here pi is the probability that a symbol is equal to the symbol I. So we can expand it as minus sum from I to 1 to L pi log to pi. L is how many symbols we have in the system. And we have one equation for the entropy is that the H actually is smaller or equal to log to L, and also is larger than 0. The entropy actually is some metric to measure how many information carried by a message. So if the entropy is 0, we can say that there is no information in this image. And when entropy reaches to log 2L, this measure carries most information. So one example is that when there are only 2 symbols in the system, and we assign the first symbol as 1 and the second symbol as 0. So we can get the entropy as 0. We could see that this message actually carries no new information, because we already know what the message contains before we receive this message. And also, if the message assigns the probability to the first symbol is 1/2, and the probability to the second symbol is also 1/2, the entropy actually reaches the maximum, which is 1. Because before receiving this message, we have no idea which symbol is more likely to appear. And for this simple case, the entropy between the probability of P1 actually has one easy curve to it's just like a half circle. And this is 0 and this is 1. The maximum is 1. In the middle point is just 1/2. So which means when the probability for the 2 symbols are equal, the entropy reaches the maximum. And when they are far away from each other, and the entropy reduces. So in this means that if P1 is near 1, so before we receive this message, we already have some idea that this message is more likely to contain symbol 1, and we can. And from the information theory, we know that H actually is the lower bound. The lower bound for the bit rate of the compression scheme. So which means if you do not want to lose information, your scheme cannot be lower than H, the bit rate. So this theorem does not tell us how to compress some content, but it provides a guideline for the compression scheme. If the compression scheme already reaches H, so we know that we do not need to put more effort to design some fancy new schemes. But if it does not, there is some room for us to improve our performance. And one example is that we have L symbols, and this is the number of symbols is the power of 2, and each symbol appears more likely, even likely. The probability of each symbol is 1/L, so we can get H is equal to log 2L. So in this case, actually we can see that the uniform length coding actually reaches the optimal performance. So we do not need to find other scheme to compress this kind of content. Okay, I think we can break for 5 minutes. Okay. Okay, let's go on. Okay. So before I talk about Huffman coding, so any questions for the stuff I just talked? So no questions? Okay, I'll talk about Huffman coding. Huffman coding actually is a practical method which can achieve near optimum performance in coding, and the coding performance actually pretty much is close to the entropy. And I use one example to explain how Huffman coding actually works. Here we have 6 symbols from S1, S2, S3, S4, S5, S6, and each symbol has a probability to appear. Here, for the first symbol, it have 5/8, and the second symbol 3/32. The next 3/32, 1/8, and 1/32. So using Huffman coding, actually it builds a tree. It first selects the 2 symbols which are least likely to appear, and combine these 2 symbols together to form a new node. And also the new node has a probability which is combination of the two select symbols. In this case, S4 and S6 has the least probability to appear. So we select these 2 and form a new node, S7. And the probability for S7 is 1/16. And then it will also assign a bit for each branch. For this branch, we assign bit 0. For this branch, we assign bit 1. And then it will pick the next 2 least likely to appear, and also combine a new node. In this case, the S2 and S7 are has 2 least probability to appear. We pick S2 and S7 and also combine these 2 nodes together to form a new node S8, which is 5/32. And then this process just goes on, and we pick S3 and S5. Oh, I forgot to assign a bit for each branch, 0/1. And this process just goes on. We pick S3, S5. And this should be S9. The performance is 7/32. And then we pick S9, S8. The node can be S10, and the combination, I also assign the bit for each branch. The combined probability is 3/8, and the process ends until we reach the probability 1, which means that we covers all the symbols in the system. So here is 1. We also assign a symbol to each branch, a bit to each branch. In order to get the code word, we just traverse from the root to each node, and we can get the code word. So for S1, we traverse from the root to S1, it's just 0. And for S2, we traverse from the root is this way. So we assign a bit here, so it should be 110. For S3 is this way, 100. And S4, 1110. S5, 101. S6, 1111. So we noticed that by doing Huffman coding, actually we obey the prefix code rule. That no code is the prefix of the other code. The reason is that for each node, actually the last branch is itself, although it shares the code with other node, but the last branch will differentiate the code, the node from others. So no node can be a prefix of other nodes. So the performance of Huffman coding actually is pretty good, in this case, we have 6 nodes. We have to use we have 6 nodes. So if we use the equal length bits for each symbol, we have to assign 3 bits per symbol. By using Huffman coding, the average bits per symbol we can compute as the expected value, which is 1 times 5/8 plus 3 times 3/32. We just compute the expected value, and the result is 1.810 bits per symbol. We could see that apply Huffman coding actually we save more than 1 bit per symbol in this case. And also, we can compute the entropy, which is minus 5/8 times log 2, 5/8 plus 3/32 times log 2. Just going. And the result is actually 1.752 bits per symbol. So Huffman coding actually saved 1 bit per symbol, and also it's pretty close to the entropy in this case. And I think Huffman coding is used by today commercialized video coding standard like MPEG-4, MPEG or H.26 series. And for Huffman coding theoretically, actually we can prove that the performance is that the performance of Huffman coding error we denote the average length of the bits per symbol, which is of course it have too large or equal to the entropy, but it can be guaranteed to be just the entropy plus 1. This is from information theory, the result from information theory. And there is also a tighter upper bound. So this upper bound is a little bit loose, tighter upper bound. So we use Pmax to denote that the probability, the maximum probability of a symbol. So when the Pmax is smaller than 0.5, the upper bound actually is HS, the entropy plus Pmax. When the Pmax is larger or equal to 0.5, the upper bound is HS plus Pmax plus 0.086. So in this case, from this upper bound and lower bound, we could see that if the entropy is high, it's like maybe 10 bits per symbol, we could see that Huffman coding is quite efficient, guaranteed by this upper bounds. But if the entropy actually is very low, I mean like much less than 1 bit per symbol, so the upper bound cannot guarantee that Huffman coding get a good performance. So there is one example is that we have 3 symbols, and the probability of A1 is very high, it's 0.95, and the probability of these 2 are very low. So using Huffman coding, we could possibly assign 1 bit to symbol 1 and 2 bits for symbol 2, 2 bits for symbol 3 and 3 bits to symbol 2, but we only get 1.05 bits per symbol. But the entropy actually in this case is 0.335 bits per symbol. So although the Huffman coding is still guaranteed by this bond, but because the entropy is much smaller than 1 bit per symbol, Huffman coding is not very efficient in this case. And also Huffman coding actually assumes that the source is identically independent. So if the source, like our common textbook, so the source are correlated, Huffman coding might not be very efficient. So here I can talk of one more scheme which apply the correlation between different symbols, which we call the dictionary scheme. So the dictionary-based scheme. The basic idea of dictionary scheme is that first we'll build a dictionary. In other words, we build a list of patterns, and these patterns must be they repeatedly occur in this message. And then we can just transmit the index of each symbol in this list. So the dictionary actually exploits the fact that certain patterns appear again and again in certain messages. So, and there are two kinds of dictionary. The first one is static dictionary, and the second one is dynamic dictionary. I use an example to explain how that static dictionary works. So we have 5 symbols to be called, and we will count how many the number of occurrence of each symbol in the message, and we count the statistic of this source. So of course, for the static dictionary, we have to have entry for each symbol itself. So and 00 for A, 001, 010, 011, 100. So we first need to include all the single symbols into the dictionary, and then because we use 3 bits for each symbol, so we have 3 more entries, and we'll compute the patterns in the source using some training sequences, and we can, for example, if we find these 3 patterns appear more often than other patterns, so we can encode these 3 symbol combination inside the dictionary, and we can assign all the code 101 and 110, 111 to these 2 symbols, to these 3 entries. To encode, we can have one general example. So, because we know that the longest length of the entry is 2, so we first read into two symbols. We read into AB, and we look up in the dictionary, and we find AB is actually 101 here. And then we read 2 more, AB. And then we read RA here. And we look up RA in the dictionary, but we cannot find RA, the entry for RA. So we just look up R here instead, and R is 100. And then we can look up AC. AC has 1 entry we can code, and it just goes on. So it's very interesting that we noticed that the dictionary's approach actually is kind of opposite of Huffman coding. For Huffman coding, we actually use the fixed length symbol, but the bits represented to each symbol is variable. I mean, the length of the bits is varying. We assign different lengths of bits to one symbol. But for the dictionary code, we can see that the bit for each entry is fixed, but the fixed length bits actually represent the variable length of symbols. And the static dictionary, I think the decoder side is also very straightforward. we could just get this, because the length of bits represent each entry is fixed, so we can just read 3 bits at the decoder side and look up in the dictionary, and we can decode the sequence. A more interesting part of the dictionary scheme is adaptive dictionary. And adaptive dictionary is known as LZ scheme. We have LZ 77 and LZ 78. It's proposed by Zever and Lamper in 1977 and 1978 separately. So these two schemes are known as LZ 77 and LZ 78. And in this class, we first cover LZ 77. It's also known as LZ 1, and this is known as LZ 2. Actually, the more popular scheme is LZ 2. In the current zip technique, also the GIF format they both use LZ 2, but we cover LZ 1 in this class. And the basic idea of the adaptive dictionary is that they do not use a fixed dictionary. The dictionary changes. They use a portion of previously encoded sequence as dictionary, and they use kind of sliding window technique. So we have two buffers. One we call it as search buffer. This is a portion of previous encoding sequence and serves as dictionary. And another buffer we call it look ahead buffer. So this is the symbols which are not encoded, and we'll search from the search buffer and match. We'll match the patterns from search buffer to the look ahead buffer and encode the look ahead buffer. So I also use an example to explain how the LZ1 works. So we have a long sequence of symbols. So there are also symbols outside, and this we refer as the search buffer, and this we refer as look ahead buffer. We know that there are 8 symbols in the search buffer and 7 symbols in the look ahead buffer. But generally, the technique, actually, the buffer size is much larger than this in order to obtain the recurring patterns, but this is just for explanation. And we also have a pointer which we call the match pointer. It moved from the last symbol of the search buffer back to the head of the search buffer. So first we have in look head buffer we have symbol A. So we move back the match point, and we find there is a match here. So we compute we actually in the adaptive dictionary part we compute a triplet, which is the offset and the length of the match, and also the next symbol after the match. So here for the match pointer, the first symbol of look ahead buffer is A. For the match pointer, we move it back, and we have a match here. And so the offset here is just it's 2. but the match length is only A, it's 1. And we leave this empty. And it may not be the longest match in the search buffer. So the match point just move on, and it records this, and it just move on, and it reaches this place, and the offset is 4, and the length of the match is 1. So it just continues moves on, and here it gets the move ahead is 7, and the offset is 7, and the length of match is 2. And it compare all these matches, so it finds the longest match actually happens here. So it just encode these two symbols into this triple as 7 as the offset of the match pointer, 2 as the length of the match, and it also encode the next symbol into so this is the code word for the next symbol. So you may be strange that why do we need to code the next symbol, because these two numbers are enough to decode the symbol sequences. The reason for encode the next symbol of the match into this triple is that sometimes there is no match in the search buffer for the look-ahead buffer. I mean that maybe some symbol does not appear in the search buffer, so we cannot find any match in the search buffer for this symbol. So we have to design a format for this case. So this case is that actually so when there is no match, we represent the symbol as just 0, 0, and the code word of the symbol. So we include this into the format in order to include this special case. And we could also compute the number of bits for each encoded symbol sequences. In that, we use S as the length of the search buffer. And W is the length of the window. So what do I mean by window is that it's actually the search buffer plus the look-ahead buffer. And also we use A denotes the size of the symbol set. So in order to transmission this triple, we actually need the number of bits. The number of bits we need is actually the upper bound of log2s plus log2w plus log2a. So you may be strange again that why do we need the w? Why can't we just use w minus s instead in order to reduce the number of bits we transmit? Because w minus s actually is the size of the look-ahead buffer. So people use w instead of w minus s because they want to cover another case, is that sometimes a match begins from the look-ahead buffer, but the match can end at sometimes the match begins at the search buffer, but it can end at look-ahead buffer. So which means that the size of this match might be longer than look-ahead buffer. Might be longer than the size of look-ahead buffer. Yeah, I think. Yeah, let me just cover one example to see why this might be true. So this is one more example. We have a window size of 13. The size of lookahead buffer is 6, and the size of the search buffer is 7. So first we have 7. 1, 2, 3. This is our search buffer, and this is our lookahead buffer. So actually it covers all the 3 cases in this example. First, we're trying to find a match to D, but we could see that there is actually no match to D. So we just encode the D as 0, 0, and the code word of D itself. And we know that this match has only, so we only encode one symbol. So we move both of the search buffer and the lookahead buffer by one symbol. So this is our new search buffer, and this our new lookahead buffer. Here we meet one common case, which is we have a match for A. Actually, we have several matches for A here. So as I have explained that we move the match pointer back from the end of the search buffer to the head of the search buffer to find the longest match. And in this case, the longest match actually is here. So the offset, the length of offset is 7, and the length of the match is we could match A, B, R, A in the search buffer. So the length of the match is 4, and also A, B, R, A, and also we code the next symbol after the match, which is the code word of R. Here we totally encode 5 symbols in this triples, and we move the search buffer by 5. So the search buffer now is here. So this is the search buffer, and we also move the lookahead buffer by 5. This is our new lookahead buffer. And in this case, we have a match for R in here, but it's not very long. So we move further the match pointer to here, and we could see that here we have R match this R, A R, R A R. So it stops here, but actually we could continue the match because the next symbol in the lookahead buffer actually is also matched here. I'm not very clear here. I think so. You could see that actually this 5 symbols R A R A actually matched here. It starts from the search buffer, but it ends at the lookahead buffer. So we also we could. So this is a third case that match begins from search buffer, but end at lookahead buffer. So we also use the triple to encode these 5 symbols, which is the offset is 3, but we match 5 symbols, and then the next one after the match is the code word for D. And by doing this, actually we can further compress the symbol sequences, and the decoding actually is very easy. For doing this, we could have this in the decoder side. So I think these first 2 are very easy to decode. So I just want to show how to decode in the third case. So this we have So now this is our search buffer, and these symbols are already decoded, and we get the triple as 3, 5, C, D, and we know that the match pointer is moved back to 3, so it points to R, and we'll first copy R into the look ahead buffer. And it move forward, and it copy A here, and it just move forward R here. And when the match pointer arrives here, it does not stop. It can just continue into the newly decoded buffer. So it just can copy this R here, and then copy this A to here, and then it decode the D, the symbol D. So actually, we can see that the third case is also very simple. If we use C language to program, it's just straightforward to copy from the previous buffer to the next buffer. And the dictionary scheme actually works pretty well when there are correlation between symbols. And actually, the authors of the LZ scheme, they prove that asymptotically, actually the performance of LZ77 could approach the entropy, and the best compression ratio that could be obtained by obtaining all the statistics of the sources. So in the dictionary scheme, actually there is no assumption for the statistics of the source, but they claim that their scheme can be as good as the best scheme, which use the full statistics of the source. And however, the LZ77 scheme actually have one assumption, in that the patterns have to be close to each other. Otherwise, it may not be very efficient, because the search buffer and look ahead buffer are just close to each other. So if the patterns repeat itself from a point far away from the look ahead buffer, it may not take the advantage of this. And I think I have 10 more minutes. And any questions for the stuff I just talked? So is it clear for the dictionary scheme? Yeah, LZW actually is LZ78. It's a variation of LZ78. Yeah. LZW is what is used in the zip. So I can talk a little bit about another coding scheme, which we call is arithmetic coding. But I may not finish it today. Arithmetic coding. The basic idea of arithmetic coding is that it codes a sequence of symbols together, but it assigns a real number to the symbol, to the symbol sequence, and then they code the real number. So there are two steps for the arithmetic coding. One that is generate a tag, which means that actually is a real number representing a sequence of symbols, and then it will assign a binary code. To the tag. I also use an example to explain how the arithmetic coding to generate a tag. And also here, in this example, we have 3 symbols, A1, A2, A3, and each symbol has a probability to appear. The probability for PA1 is 0.7. The probability for PA2 is 0.1. The probability of PA3 is 0.2. And suppose we encode this sequence, A1, A2, A3. We encode this sequence together. So they generally use one. So we draw one line from 0 to 1, and we know that from 0 to 0.7, because A1's probability is 0.7, and this segment represents A1, and this segment 0.8 represents A2, because A2 has the probability is 0.1, and then this segment represents A3, and so we just get this segment and enlarge it here. So this segment starts from 0 and end at 0.7. And still we use the same technique. We assign 70% of segment to A1. So it's 0.49. And here is 0.56. And then the other segments are assigned to A3. And here we want to actually try to code A2. So we select this segment and enlarge it here. And this segment starts to 0.49 and end at 0.56. So and again we assign 70% to A1, which is 0.539. And here is 0.546, and we'll choose this one. It will start at 0.546 and end at 0.56. And actually, we only code 3 symbols, and we can pick any real number inside this segment to represent these 3 symbols without any ambiguity for the decoder side. So generally, we can just assign the midpoint of this symbol, which might be 0.553, 553, and we have no ambiguity. So why is that? For example, in a decoder side, we use the number of 0.553, and in the first step we are asked that we know that A1 belongs to 0 to 0.7, A2 belongs to 0.7 to 0.8, and A3 belongs to 0.8 to 1. So this real number actually falls into the category of A1. So we decode the first symbol as A1, and we select this range, enlarge it. So from here, we could know that the second symbol, if it's A1, it will fall into 0.49, and A2 will fall 49 to 0.56, A3 from 0.56 to 0.7. Again, we compare this. We check which category this real number falls, and we can see that it falls into the category of A2. So the second symbol can be A2, and then we further expand the A2's category as the third symbol. We have a range for each number, and we could either check it, and we could get this real number actually falls into the category of A3. We can decode the third symbol as A3. And after getting this real number, we'll have to assign bits for this real number. The scheme used by arithmetic coding that is first decide the length of the bits to represent this real number 0.553. It represents the symbol A1, A2, A3. So it assumes that the source actually is IID. So it can easily to compute the probability that this symbol appears, which is equal to just the product of the probability of these 3 symbols, and we could get one number. which we call px. And the number of bits assigned by this to this real number is just equal to log 2 1 over px plus 1 bits. So we use so many bits to represent this real number. And they also actually prove that by using this, it can uniquely generate a bit sequence for each real number. So in our example, we have px actually is equal to 0.014. So the number of bits we could compute is 8 bits. So we can get the binary representative as 0.553. We write it in the binary case, it's just 1 over 2 plus over 5 plus over 6 plus 1 over 8. So which is equal to 0.1001101. So we use 8 symbols, and we only use 8 bits to represent this real number. So the bits we use to represent the 0.553 is just 10001101. And the theorem tells us that actually the average length of the arithmetic coding is, of course, it should be larger or equal than the entropy, but it's smaller or equal to entropy plus 2 over m, where m is the length of symbol sequence. So we can see that if we increase the length of the symbols, actually we can asymptotically approach to the lower bound entropy. So which makes the arithmetic coding interesting. Okay, any questions for the arithmetic coding? Okay, I think that's for today. Thank you for attendance.
The same as the MMSE. Okay. For any other distribution and Gaussian distribution that has the same mean and covariance, their LLSE are the same, right? Because the estimate, as we seen just now, depends only on the mean and the variance. If two distribution has the same mean and variance, their LLSE estimate are the same. Okay, Gaussian is just one of the case. So they are the same. And then for the other, LLSE is suboptimal. Is worse. I mean, it's worse than the MMSE. Okay, so now you can see the LLSE. First, it is very easy to implement, because everything is linear. You can implement by a linear filter. Second, it gives you some bound on the on the minimum mean square error. Okay, then that means although I cannot get a very accurate estimate here because it's a very hard problem, I can do a simple one and the one I get is a bound of the problem I cannot solve. So people are satisfied by this argument. That's why the LLSE are so useful in reality. Okay. So in summary, in this lecture, we have reviewed what is the problem of the image restoration. Your image is degraded by some noise, and then you pass through a linear filter to restore it. And then we discussed the problem. Okay, the image itself is not globally stationary, so we should do everything in local. To do everything in local, we need to estimate the mean and the variance of the original image. To do that, we do some modeling, and then I hope I show you that although we cannot get these two directly, we can estimate using the ML estimation, maximum likelihood estimation. And then by plugging those two things into the filter, we get a Fornell filter that meets our intuition in the extreme case that your signal to noise ratio is extreme large or extreme small. Okay, and then we explain it why this makes sense from the intuition, and both from the intuition and from the resulted equations. And then we we discuss how we can change the problem formulation to get other interesting results. For instance, the power spectrum filter that keep your power spectrum the same for F hat and F. Also, we can change the linear function constraint to get want to get some result for MMSE. Although we didn't get some result for MMSE, we get a better understanding why LLSE is so useful in reality. Okay, so I think that's it. Any questions? Okay, that's all for today. Thank you.
Model for a P sub f and estimate the parameters of that model. It's called parametric modeling. Okay, parametric modeling of spectral of the spectrum. And in fact, there's a chapter 6 in Eennlb that we skipped, but that thing is all about spectral estimation. So estimate parameters of P sub f by observing. By observing what? The only thing we got to observe is what? Just G. There's nothing else. By observing G, right? So as if there's not enough bad news, there's one more bad news on top of that. So let's say we kind of shove under the rug and we compute some sort of a P sub f and P sub w. What's the last bad news for today? And that is, most images are not stationary, okay? Images are only locally stationary. So what does that mean? That means if I look at, let's say I took a picture of my field of view. I took a picture of what's in front of me. If I go to the white wall there and don't look around and just, actually I'll do an experiment here. If I just look here, yeah, I'm looking stationarity. If I don't know where in the board I am, right? But if I step back a little bit here, oh, I sure as hell know where I am. I see the board, and there's edges, and there's all kinds of non-stationarities going on in images. So that messes things up further. But as you'll see in the next, so another problem is that images are not really stationary. But we can solve that problem in the sense that they are locally stationary. They're not really globally stationary, but they're locally. So maybe we can devise local adaptive Wiener filter, which is what we do next lecture, in order to do this. Anyway, I hate to leave you without showing at least one picture of Wiener filtering after I took you through so much derivation. So this is the end of really the end of the lecture. Okay, so this is can you zoom in, please? This is the picture of figure 9.5 of Eennlb's book. Okay. Okay, so on the top you have this U.S. Air Force undegraded 512 by 512 picture. This is one of the pictures that my friend Throasos was processing when we were both grad students. This is the degraded image after a bunch of noise has been added, and I really have to go back and forth for you to see it. Without noise, with noise, and this is with Wiener filter. And the first thing that you notice, if you had the book, the most striking thing is that, yeah, a little bit of the noise in the background has been blurred here, but the U.S. Air Force sign is pretty much blurred here. So Wiener filter has blurred out our signal. And we'll talk about how we can fix that problem if we do the locally adaptive Wiener filter next time. But the principles kind of still stand correct. Okay, very good. Enjoy your spring break, and if you want, pick up the solution to the homework on your way out.